Hi there, in this video we're going to be going through applications of logarithmic functions. So this is the last video where we're going to do some questions that show where logarithmic functions could apply to some real life situations and how we would solve those kinds of questions. So if we look at the syllabus, we're looking at this last one here, identify contexts suitable for modeling by logarithmic functions and use them to solve practical problems. So sometimes it's the hardest one, but I'll show you that this isn't too tricky, this section. So there are stacks of applications for logarithms in real life, a lot. So we've got a few here, the magnitude of earthquakes. So I'm going to do an example with earthquakes and the Richter scale. The intensity of sound is measured using a logarithmic scale. Acidity of solution in chemistry. So any situation where something grows quickly and then tails off might be a good model for a logarithmic function. And this is essentially what mathematicians do. They get physical phenomena, physical situations, and they try and fit a model to that situation. So you might get some data about something, and it might turn out that a logarithmic function is the function that best fits that data, and therefore you can analyze it, extrapolate, and interpolate in the data using this function. Mathematicians do a lot of this. So in this one here, it's a little bit boring because I'm going to give you the model. And then we have to just work out, given that model. It would be more realistic to give you some data and ask you to come up with a model for that data. So we're not doing that here. In exams, you're going to be given the model to start with. So yeah, we're looking, let's talk about the Richter scale to start with. That's a real common one. The Richter scale measures the intensity of earthquakes. So as you can see here, we had some really dodgy ways of measuring it before, like the number of chimneys that fall down and all that bad stuff. So we've got a scientific measurement now, and it comes from this formula here about the magnitude. It's the ratio of the logarithm of the intensity of the earthquake, which is this bit here, compared to a standard intensity, which they're calling x naught. So you have a seismograph reading the shaking of the ground, a very, very, very precise instrument. And the x naught part is a reading of 0.001 millimeter, or it's 0.0001 of a centimeter at a distance of exactly 100 kilometers from the epicenter of the quake. So all the seismographs we have are calibrated to this scale here, so we can get an accurate reading of what the force or the magnitude of the earthquake is. So let's have a look at this one. The San Francisco earthquake 1906 would have given a seismographic reading of 7.943. That is this distance here. So what was its magnitude? So the magnitude of the earthquake is log, and Richter used log base 10 of, in this case here, we've got a reading of 7.943 compared with the standard 0.001, and this was in millimeters. These are both millimeters. Okay, so that gives us the magnitude of the earthquake. So if you do that, 7.943 divided by 0.001, that's going to give us 7943, and log of that is 3.9. Okay, so the magnitude of that one there is 3.9. So that's a pretty fairly small earthquake. So here's another earthquake example here. We've got an earthquake that measured 8.3 on the Richter scale, big earthquake. And the same year there was an earthquake in Chile that was 4 times stronger. Now what we need to realize here is if we're using a logarithmic scale, then an earthquake magnitude 6 is 10 times more intense than an earthquake magnitude 5. So every time we go 1 up the scale, it increases by an order of 10. If you remember that logarithmic scale that we had when we first introduced logarithms, base 2, it looks something like this. Okay, so you can see the scale expands out. So this is each time we're going a factor of 2 bigger on the log base 2 scale. On the log base 10 scale, this number here is 10 to the power of 1, this number here is 10 to the power of 2, this number here is 10 to the power of 4. So you can see a earthquake magnitude 3 on the scale is like 1,000 compared to an earthquake magnitude 2, which is just 100. So the scale gets really, really big, especially as you get up into the bigger numbers. So there's a really big difference between an earthquake magnitude 8.3 and 8.8. That's many, many, many times bigger. A lot of people don't really understand how that scale works. So let's work this out. I'll show you how the maths works out, and you will be a more informed citizen after this. So this earthquake measured 8.3, and we're looking at one that was 4 times stronger. So let's put the numbers in the formulas and I'll show you how to solve these. So the magnitude, log base 10 I, so this is the intensity of the earthquake over the standard one. And we know for the first New Zealand one, the magnitude was 8.3. If we look at the other one, log base 10 I over S is equal to 4 times. So this value here, the intensity of the earthquake, I'm using I for the intensity of the earthquake. It's actually the seismographic distance on the seismograph. But this one here was 4 times the New Zealand one. So instead of writing I there, I can write that is 4I. Okay. So really what I want to know is what was the magnitude of the earthquake for this one that was 4 times the intensity. Okay. If we look at the equation, the top equation there, we know some log rules. Log A over B is log A minus log B. So that is, I'll just call that log S, and that's 8.3. So just use that log law, and if I do that for the same as the second equation, I get this, log S, and that's equal to X. That's the thing that we're trying to find. We don't know what that magnitude is. So if we now have 2 equations and we're trying to solve these equations, we need to solve them simultaneously. Now you can see if I add the equations, that's not going to work, but if I subtract them, okay, if I say this is equation 2 and this is equation 1, if I say equation 2 minus 1, these 2 terms here will disappear, won't they? Negative log S minus negative log S is negative log S plus log S. Those 2 terms will disappear. So we'll end up with log 4I minus log I is equal to X minus 8.3. Okay, that's good. Now, on the left-hand side here, log A minus log B is log A over B. Okay, that's that log law there. Log A minus log B, log A over B. And that gives us X minus 8.3. We're nearly there. Now this is the good bit right here, is these 2 here cancel out. So we're left with log 4 is X minus 8.3. And the final step, X is log 4 plus 8.3. And now I can get my calculator out and work that out. Remember, this is log base 10 as well. So log of 4 is my answer, plus 8.3. I always do it in 2 steps. So the answer is 8.9. Okay, so the magnitude of this Chile earthquake that was 4 times as intense of an 8.3 quake was 8.9 on the Richter scale. So you can see you've only moved up a little bit, but the intensity of the earthquake is massively 4 times greater. So have a go at this problem here. We've got an earthquake that measured 7.1 on the Richter scale. How many times more intense is an 8.3 quake compared to a 7.1 quake? So use the same equations, go through a similar process and see if you can work that one out. So this example here, we've got an equation that we're given. It's about a marine biologist measuring the length of a whale calf 1 month after birth and 6 months after birth. So they've done 2 separate measurements. And we've got a formula here for what she believes is the correct model for the first 12 months of the length of a whale. So we've got this logarithmic equation here, 20 log base E, so ln, t over a plus b, where a and b represent positive constants. Now, you would not be asked to draw this kind of graph because it's a little bit outside the syllabus. This 20 here at the start of what it does, but that just stretches it up. But you wouldn't be asked to draw this one here. So there's a lot of technology going on in this particular example, so I'm going to show you the answer. So first of all, we want to find A and B. Now I'm thinking here that we're going to have simultaneous equations, because to start with, we're going to substitute in the length 2.1 here, and this is in months. Okay, 20 ln 1 over A plus B is 2.1, and then 20 ln 6 over A plus B is 5.2. Okay, and then we have some simultaneous equations that we can then solve. You can see on the calculator the way that you might do it here that might be a little bit easier. So to find the function LT, say that L1 is 2.1 and L of 6 is 5.2, given that A and B. So we're going to solve for A and B, and you see the calculator does that automatically. Or you could write the equations down as I just read out, and it gives you A is 26.85, B is 1.0735. Okay, so there we've got our two values of A and B. Again, definitely want to use our calculator. This is definitely in the calculator section. So here's a way that our calculator really could help us here to solve this one. Secondly, it says let's do the graph. Okay, so again, using our calculator, we could create a graph of this, not in the non-calc section, but we could certainly trace out the graph of this function and do some analysis on that, which will be really handy. So the question then says, plot the graph of LT, and then we might want to say what's going on at 0. Okay, so what's the predicted length at 0 when the calf comes out? So we can see on the graph there's 0, 1.4179. So the calf's born, according to this model, it's about 1.4 meters long when the calf is born. Determine the predicted length of the whale calf after 5 months, correct to 2 decimal places. So we just need to put our cursor and get along here to 5, and then we will see what that is. And if we do that, or we can just work in main as well, we've got the definition of the function, and we just say what's L of 5, and we get 4.62 meters long. And lastly, predict how many months it would take for the length of the whale calf to be 3 meters. Give your answer correct to 2 decimal places. So here we've got our function, and we want to know when is this equal to 3. So we're solving L of t equal to 3, and the variable is t. So you could just type the whole thing down. You could just drag this down into there as well, solve this equal to 3, and we get 2.37. So around about 2.37 months we're predicting it will be 3 meters long. So that's some basic idea of how you would use a log formula in context in a real life situation, and it's kind of similar to what we've done with other functions, but this one particularly to do with logarithms.